All right, this is week 9, and I'm going to go through some comparison functions, but I also wanted to step back and just go through a few basic tools in SysMac. Now, when you're starting to do your programs, you may find, for example, let's put an input in here, and we'll give it a name, but I won't put an output on this line. Now this is an extreme example. So I write this program, but I'm missing some outputs. Right off the bat, I've got a red line down here, which tells me there's an error on this line. There's a tool right here called Build Controller. And if I run that, what that will do, it simulates you sending it to the PLC. But what happens is, it'll give you the error. So before you try and transfer your program, build it, and if you've got any errors down here, it's not going to run. So you've got to open this up so you can read the error. Inputs must not be connected to the right bus bar. Correct, I've got no output. If I put an output in here, right click, insert an output, and there, now I've got an input and an output. If I run my build now, first off, the red bar is gone. So that rung is now acceptable. It's been tested. It doesn't mean I'm using the right inputs and outputs. It just means it's configured right and can be downloaded. So if I run a build, my errors are gone. If you get a yellow triangle, a warning, it will still transfer. It's just not happy about it. So there's one basic thing. Remember, here's something you cannot ever do. You can never, ever have two outputs in one rung. It'll never work, A, because in reality, if this was a ladder diagram, and this was a 24-volt source, two outputs in series would mean that each of them only get 12 volts, so neither one would work properly. Again, if I build this, that's weird. Trip point. It thinks this is an input, and it's just a variable. But that will not work. It may let you download, but if you've got these, your program will not function correctly. So you'd have to get rid of one of these and just delete it, and then insert a second input. And again, once the rung's correct, now it would actually process and run. So that's a handy tool. And again, click on variables. They're the ones I created. Bill, Bob, and Joe, data type Boolean. By default, they'll go as internals. Here are some that are in the data conversion program. And if I didn't want to leave them in here, in the margin out here, right click, move to global. Because if you're going to be dealing with the HMI, which you are, they can't be internals. The HMI cannot read internal variables on the PLC because it's considered external to the PLC. And then once they're all loaded in here, now your program could work. So I can close that, get back to your program. Now, what I really want to do is go through some more of the comparison functions. So if we go to our toolbox, we've got the usual less than or equal. This one is called not equal, equal to, greater, greater, or equal to. And these are duplicated rather than the symbols. You get the same functions here, equal to, less than or equal to, greater than. And the same thing will occur. You can put these up here. I can get rid of those. They will have an output. And again, you can hit the help key. Go to instruction, or just press the F1 key. And up here are all the comparisons. And they're all listed, and then you can actually zero in on these. So for less than, and this gives you all the basic functions. It'll describe the function, show you the graphical. Here are the inputs. You can add more inputs. And what it does, it checks them all in sequence. Input 1 must, if you have more than 2 inputs, input 1 must be less than input 2, which must be less than input 3, which must be less than input 4, and so on. If they're all true, the output is energized. So you can see it here is the logic. You can check the logic function, and then usually down below they give you more information about the data types that it can use, comparison of data. The valid range depends upon the data type. So your inputs, they can't be Boolean because they're not off or on. It's going to be a number. So it'll be integer or real or something else. You can actually use strings, bit strings, integers, real numbers, time, date, time of day, etc. All of those things are available to compare. And it gives you more of the instruction. And then usually they show you a couple of examples to show you the format. If you're using integers, again, int hash and the number, and then some kind of an output. And it says the less than or equal instruction determines that if input 1 is less than or equal to in2, which is less than or equal to in3, then it's true and the output will be energized. So you can check that sort of a sequence with these. Different data types, of course, int, integer, double int, long integer. They cannot be compared to unsigned values because int has 15 bits, but an unsigned int is using all 16. So they're just saying use the same, compare apples to apples and ints to ints. So it's handy, helps you get through. So there's our integer. So all those basic functions. You also have the ability to compare ASCII values. ASCII values are just a numerical code for letters. So you can spell out a message, and each letter will be converted to a number. And that's actually how they compare them, because they're just comparing the total value of the numbers. Because computers don't recognize letters. They got to convert it to a number, and then they can see whether it's bigger or smaller or equal. And again, if they're all true, and again, you can right-click, put another input in, you can remove an input, and check the logic. So if it's strings, the example could be, and they'll show you an example here. Let's go back and look at an ASCII string. They give you the format, so scroll down and look at the example. 3 input, less than or equal to ASCII string. So they just use 2 letters, but it could be 10 letters, could be a sentence, could be anything. But AB is less than AC, which is less than or equal to AC. So this is true. And again, these are all converted to number strings because it's ASCII. ASCII characters, again, just a numerical code for letters. So the comparisons, there are a lot of them. You can compare tables, entire tables, all of the numbers. So that's one type of value. And there's a PowerPoint that I'm going to be putting up there Now, the next thing, a bit of a review, we could look at BCD. You will come across some of these older devices. This was a forerunner to HMIs. People or operators could put set points on a machine using little number wheels, and the thumb wheels, they'd set the number. Maybe they wanted a run of 340 units of some particular device that they're making. So they would key in 340, and the machine would run until it counted that many parts, and then it would shut off and put up a finish light or something like that. So binary coded decimal is one way. A lot of thumb wheels have them, and a lot of displays used to use them. Now it's a lot easier to just use an HMI, but you will come across these. So binary coded decimal, each digit is converted to its binary number. 6, so this is 1, 2, 4, 8. 2 plus 4 equals 6. 3 is 1 plus 2. There's our 1, 2, 4, 8 bits. That's the 8-bit. And 1 and 4 add up to give us a 5. So BCD, going a little farther, hexadecimal. A lot of machine code is written in hexadecimal because with each character you can get more number choices. So instead of base 10, which is decimal, we count 0 to 9 and then it rolls over. So that's 10. Hexadecimal counts from 0 to 15 and then rolls over. But we only have digits in our Latin-based numbers for 9, 0 to 9. So then we flip to letters. So we go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. So that gives us a total of 16 values. So in hexadecimal, again, it's still all converted to binary. If this was an F here, it would be 1, 1, 1, 1. So some systems, like thumb wheels or displays, used to become hexadecimal. The way you convert from decimal, which is our numbers, is the first digit is 6 times 16 to the power 0. The second one, D times 16 to the power 1. D is actually 13 in decimal. So 13 times 16, that D is worth 156. 2 is 7. Oh, they got a typo here. That should be a 7. 7 times 16 to the power 2 is 16 to the power 0, power 1, power 2. And then you add them all up to get a decimal number. So to convert decimal value of 610 into hex, it would be 2d6. Now, PLCs, of course, that's just a very bare bones bit of math. So if you do have to do some of that value, they have built-in functions to do the conversion for you. So you can get data type conversions. And you can convert all kinds of things. This is alphabetical. So double integers to double word, double integer to int, double integer to real. If we scroll down, we get double words, which is 32 bits. And here we go, integers to double int, integers to real, integers to long word, etc. And all of your conversions are done in here. So this works sometimes when you get an input that you have to use, but you want to convert it to integer, but it comes in as a real number. Analog inputs use real. But if you just want to use that in some program that's already set up to use integers, you could do a conversion, convert real to integer. Typically what that does, it truncates all the decimal points off. But there are some mathematical conversions that will happen there too. You can also switch, where is it? It should be decimal. They don't have decimal to hex. There might be some under conversion. Hex string to numbers. Again, a lot more conversion types, most of which you'll never use. Hex string to number, and tons. Binary to gray L word, long word. So all kinds of conversions.